Hi everyone, welcome back. In this video, we are going to learn Java object-oriented programming concepts in 1 hour, designed as a complete interview guide with real-world examples. If you are preparing for Java interviews, then this video will help you understand the most important OOP concepts in a clear and practical way. We will start with basics like classes and objects, and then move to constructors and access modifiers. After that, we will cover core concepts like abstraction, encapsulation, and inheritance with simple examples. You will also learn method overloading, immutable classes, and important keywords like this and super. And finally, we will understand an important interview question: why Java is not 100% pure object-oriented. The goal of this video is to help you understand concepts quickly and explain them confidently in interviews. Let's get started. Let's understand Java classes and objects using real-world examples that you can actually visualize. Forget the code for a moment, just imagine these scenes with me. First, think of a blueprint of a house. A blueprint doesn't have walls or paint, it's just a design. It tells us how the real house should look. That's exactly what a class is in Java. It's a design. Now picture 3 actual houses built using that blueprint, one painted yellow, another with a red roof, and one with a swimming pool. Each of these is different, but they all came from the same blueprint. Those are the objects. In Java terms, class is the blueprint and object is the real house. Next, let's take one more real-world example, a car factory. On the wall, there's a design sheet showing the parts of a car. Engine, wheels, color options, top speed. That sheet is like a class. Now imagine the assembly line. One car comes out in red, another in black, another in silver with sunroof. Each of these cars is an object, real, usable, and unique. They all follow the same design, but have their own values. Class is the car design. Object is the actual car built from it. Next, let's take one more real-world example. Mobile phones. Imagine you are in a store, you see an iPhone, a Samsung, and a Nokia. Even though the models are different, they all follow the concept of a mobile phone. So in Java, we define a mobile phone class with properties like brand, model, price, and battery life. Then we create objects like iPhone 14, Galaxy S24, or Nokia 3310, each with different values but all following the same class. Easy, right? Now let's see what exactly a class is in Java with an example. In simple words, a class is a blueprint. It defines what data an object should have and what actions it can perform. Think of it like an architect's design for a house. The blueprint is not the house itself, it's just the plan. But you can use that plan to build many houses. In Java, a class contains variables which are called fields and methods, which define what the object can do. Let me give you a real example. Let's say we want to represent a car in Java. We can create a class called car. Inside this class, we define some fields like brand, color, and speed. We can also define some methods like start, accelerate, and stop. Now this class doesn't represent an actual car yet. It's just a blueprint. To create a real car, we need to create an object. So what is an object? An object is an actual instance of the class. It holds the real values and behaves like a real thing. You can create many objects from one class, just like you can build many houses from one blueprint. For example, we can create a car object called car1 and give it the brand Toyota, the color red, and speed 80. Then we can create another car object called car2 with a different brand and speed. Each object has its own data, but all follow the same structure defined by the class. Now how do you define a class in Java? Very simple. You write the word class followed by the class name, and then you open the curly braces. Inside the braces you write your fields and methods. Let's take an example. We create a class called car. Inside the class we define 3 variables: brand, color, and speed. Then we create a method called start. This method will print car is starting. This is our blueprint. Now how do you create an object? You use the new keyword. For example, you write car1 equals new car. This creates a new object of the car class and stores it in the variable car1. Now, to access the object's fields or methods, you use the dot operator. For example, car1.brand equal Toyota, car1.start. This will call the start method. It's like saying, hey car1, please start. This is how classes and objects work together in Java. Let's now look at a quick recap. A class is a template. It defines the data and behavior of a type. An object is an actual instance of the class. It stores real values and can perform real actions. You define a class using the class keyword. You create an object using the new keyword. You access the object's members using the dot operator. That's the core concept of Java classes and objects. So what is a constructor? A constructor is a special block of code that runs automatically when you create an object in Java. Think of it like the blueprint that sets up your object. Whenever you use the new keyword to create an object, Java calls the constructor. Now, let's understand what makes a constructor special. First, the name of the constructor must be exactly the same as the class name. Second, it does not have a return type, not even void. This is how Java knows that this is a constructor, not a regular method. So why do we use constructors? The main purpose of a constructor is to set initial values to the object's fields. In simple words, it helps us set up the object when it is created. Let's take a real example. Imagine you want to create a student class. This class should store the name, age, and grade of a student. We write a class called student. Inside this class, we declare three variables, name, age, and grade. Now we define a constructor. The constructor also has the name student. It takes three parameters, a string for the name, an integer for the age, and a character for the grade. Inside the constructor, we assign these parameters to the class variables. So the name field gets the value of the parameter n, the age field gets the value of a, and the grade field gets the value of g. Now when we create a new student object, we pass the values. For example, Ravi 20 and grade A, and the constructor will automatically assign these values to the object. Let's now talk about the types of constructors in Java. There are mainly two types, default constructor and parameterized constructor. First, the default constructor. This is a constructor that takes no arguments. It just assigns some default values to the fields. For example, let's take a class called dog. Inside it, we declare a variable called breed. Then we write a default constructor with no parameters. Inside the constructor, we set breed to German Shepherd. Now when we create a new dog object, the breed will already be set to that value, even if we didn't pass anything. It's like creating a phone that comes with default settings. You didn't customize anything, but it's ready to use. Now the second type, parameterized constructor. In this constructor, we pass the values while creating the object. Let's go back to our student example. The constructor takes name, age, and grade as parameters. So when we write new student Ravi 20A, all these values go into the constructor and the object is set up instantly. It's like ordering a pizza with your own toppings. You tell exactly what you want and it's made that way. Next, let's talk about constructor overloading. In Java, we can create more than one constructor in the same class as long as the number or type of parameters is different. This is called constructor overloading. For example, suppose we have a book class. We can have one constructor with no parameters, one constructor with only the title, and another constructor with both title and author. Java will automatically select the correct constructor based on the arguments passed. This gives you flexibility. You can create the object with minimum details or full details, your choice. Now let's talk about some common mistakes developers make with constructors. Number 1, don't write a return type in a constructor. If you write void or anything else, Java will treat it as a method, not a constructor. Number 2, make sure the constructor name matches the class name exactly, including capitalization. And number 3, always use the new keyword to call the constructor and create the object. Let's also do a quick comparison between constructor and method. Constructors run automatically when you create an object. Methods only run when you call them directly. Constructors don't have a return type. Methods always have a return type even if it is void. In simple terms, constructors are used to build and prepare the object. Methods are used to perform actions or behaviors on the object. Finally, remember this. Every object you create in Java starts with a constructor. It's the starting point. Whether you use the default one or write your own parameterized version. Constructors help you set up your data cleanly and reliably. That's the complete picture of constructors in Java. Hi everyone, welcome back. In this video, we'll talk about abstraction in Java, and we'll begin with a real-world story to help you picture it. Let's start with something simple. Think of a car dashboard. When you sit in the driver's seat, what do you see? A steering wheel, pedals, buttons, and a gear stick. You press the accelerator, the car moves. You turn the steering, the car turns. But do you ever see how the engine actually works? Do you understand how fuel gets injected, how the pistons move, or how the crankshaft turns? Nope, you don't need to. All that complexity is hidden from you, and that's the beauty of it. What you do get is a simple interface to drive the car. That's abstraction in real life. Only the necessary parts are shown to you. The rest, the complicated machinery, is hidden. Now let's bring this idea into Java. In Java, abstraction means hiding the internal implementation details and only showing the features that are relevant for the user. You define what an object does, not how it does it. You focus on the functionality, not the internal logic behind it. So how do we achieve abstraction in Java? There are two main ways. One using abstract classes and two using interfaces. We'll start with an abstract class. Let's say we are building a system for payments. We have a common structure, whether it's a credit card, a debit card, or UPI. So we create an abstract class called payment. Inside this class, we define an abstract method named makePayment. This method doesn't have a body. It's just a declaration. Why? Because we want each payment type, like credit card or UPI, to provide their own version of how the payment is done. We are only defining what should happen, not how. Now let's build this out fully. We create two subclasses, one called credit card payment and another called UPI payment. Both classes extend the abstract class payment, and they provide their own implementation of the makePayment method. In credit card payment, we might simulate entering card details and processing through a gateway. In UPI payment, we might simulate entering a UPI ID and confirming with an OTP. So the calling code just needs to say, hey, make a payment. It doesn't care how that payment happens behind the scenes. This is the power of abstraction. Imagine later you add PayPal or wallet support. You just create another class that extends payment and defines its own makePayment method. The calling code doesn't change at all. That's abstraction in action. It hides the complex logic and only exposes what's needed. Just like you don't need to know how a car engine works to drive it, you don't need to know how a payment is processed internally to trigger it in code. That's why abstraction is so important in Java and in real-world development. It simplifies how we think about systems. It lets us work with interfaces rather than implementations, and it makes code easier to manage, scale, and update. So we were talking about abstract classes. Now let's take the idea a step further and understand abstraction using interfaces. Let's say we have an interface called vehicle. This interface defines what a vehicle should be able to do, like start, stop, and accelerate. But here's the key. It doesn't say how these things are done. So now, if a class like car implements the vehicle interface, it must provide the actual implementation of those methods. Same goes for a bike or a bus. Each vehicle knows how to start and stop, but they all do it differently. So the interface simply sets the rules. It defines the what, not the how. This gives you the freedom to change the internal logic of each class without changing the interface. You are separating the idea from the implementation. That's the beauty of abstraction. Now let's quickly understand why abstraction is so useful. The first benefit is simplicity. Abstraction lets you work with high-level ideas instead of getting lost in details. When you use an interface like vehicle, you don't care how each class handles acceleration, you just call accelerate, and it works. The second benefit is flexibility. You can switch out implementations easily, maybe replace a car with an electric car without affecting the rest of your program. The third is security and control. Abstraction hides unnecessary details, which reduces the risk of misuse and keeps your design clean and intentional. Now let's address a very common confusion. What's the difference between encapsulation and abstraction? Encapsulation is about protecting data. You put your variables inside a class, make them private, and give access only through public methods like getters and setters. It's like locking your valuables in a safe and giving people keys, but only for certain rows. Abstraction, on the other hand, is about hiding complexity. You define what should be done, but hide how it's done. Think of it like the buttons on a washing machine. You press start and the machine takes care of the rest. You don't see the wiring or the water levels, just the result. So in short, encapsulation protects the data and abstraction hides the logic. They often work together, but they solve different problems. Let's wrap this up with a quick recap. Abstraction is the idea of showing only the essential features and hiding the details. We use it in Java with abstract classes and interfaces. It helps us design flexible, secure, and scalable systems. It separates the what from the how, just like a car separates the steering from the engine logic, and it makes your code easier to maintain and extend in the long run. Thanks for watching, and I will see you in the next Java lesson. Hi everyone, welcome back. In this video, we will discuss encapsulation in Java with real-world example. Let's start with a quick story you can easily imagine. Think of your ATM card. You use it every day to withdraw money, check your balance, or maybe change your PIN. But here's the catch. You never see how the machine connects to your bank, how the validation works, or how the transaction is processed in the back end. You just press a few buttons and it works. The ATM hides all the complex stuff from you. That's what we call encapsulation in real life. Hiding the internal details and only showing what's necessary. You get the service without knowing how everything works inside. And now let's take this concept into Java. In Java, encapsulation means we keep the internal data of a class safe and hidden from the outside world. We wrap the data like variables and the code that modifies it like methods inside one single unit, the class, and then we control access to that data. We don't allow anyone to change it directly. Instead, we give them getters and setters. These are public methods that allow controlled access to the private data. So think of a class like a locked box. Inside the box, you have your private data. Outside the box, you only expose the keyhole, the getter and setter methods. Anyone who wants to read or change the data has to use those keys. They can't break open the box and directly mess with what's inside. This protects your data from accidental or harmful changes. Let's understand this better with a complete example. Imagine a class called student. Now a student has two pieces of data, a name and a roll number. We want to protect this data from being directly accessed or changed from outside the class. So how do we do that? We start by declaring both variables as private, like private string name and private int roll number. This means no one outside the class can directly touch these variables. These variables are also referred to as instance variables. Next, we create two public methods called getters that allow someone to read the values. One method is getName to read the student's name. Another is getRollNumber to read the roll number. But reading alone isn't enough. We also need to allow safe updates. And that's where setter methods come in. We create a method setName string new name, which sets the name of the student, and a method setRollNumber new roll number, which sets the roll number. Now whenever someone wants to change the student's name, they have to call these setter methods to update the private instance variables. You can't directly change the instance variables because they are private. This gives you a safe point of control. For example, inside the setName method, you can check if the name is not empty before setting it. And inside setRollNumber, you can validate that the roll number is a positive number. This keeps your class data clean, secure, and predictable. So now you've fully encapsulated the student data. It's wrapped inside the class and only accessible through carefully controlled methods. That's encapsulation in action. Let's come back to the ATM for a second. You don't directly access your bank's database, right? Instead, you use a touch screen or a few buttons. Those are like getters and setters. You enter your PIN. If it's valid, the machine allows the transaction. The logic behind it, like checking the balance applying limits, or printing the receipt all stays hidden inside the system. Java does the same thing with encapsulation. It hides the logic and exposes only what you need. Why is this so important? Well, imagine if your variables were public and anyone in your code could change anything at any time. That would be chaos. One part of your code might accidentally set a negative age to a user, or update an account balance to 0 just because of a typo. By using encapsulation, we prevent this kind of damage. We make our data more secure, reliable, and easier to manage. Here's another cool benefit. Encapsulation helps you change your internal logic later without breaking other parts of your code. Because the internal code stays hidden, only the public methods are used everywhere. So if you ever need to change how getName works, you can do it, and the rest of your code won't even notice. That's called loose coupling, and it makes your code much easier to maintain and scale. Let's quickly recap with a real-life visual. Picture a coffee machine. It has a few buttons: espresso, latte, cappuccino. You press a button and get your coffee. But you don't know how the machine mixes the ingredients, how much milk it pours, or how long it brews. All of that logic is hidden inside the machine. Java does the same with classes. It hides the internal process and only shows the external interface. That's exactly what encapsulation is all about. So in short, encapsulation means hiding data using private variables. We access or modify that data through public methods known as getters and setters. This protects the internal state of the object. It gives us better control, security, and clean structure in our code. Just like the ATM or the coffee machine, you interact with simple buttons, not the internal wiring, and that's what makes your Java code professional and reliable. Thanks for watching, and I will see you in the next Java lesson. Hi everyone, welcome back. In this video, we'll learn about inheritance in Java, using a real-world story to understand it clearly. Let's begin with something you have seen since childhood: your family. Think of your father. He has certain traits like height, eye color, and maybe a good singing voice. Now think about yourself. You might have inherited some of those traits from him. You didn't create them from scratch, you received them. That's inheritance in real life. One generation passes down features to the next. You still have your own unique identity, but you also get access to what was already there. Now, let's bring this concept into Java. In Java, inheritance is a mechanism that allows one class to acquire the properties and behavior of another class. We call the existing class the parent class or superclass, and the new class that inherits from it is called the child class or subclass. Let's say we have a class called vehicle. A vehicle has a speed and a color, and maybe a method to start the engine. Now imagine you are building a class called car. A car is a type of vehicle, so it already has speed and color, and it also needs to start the engine. Instead of writing all that code again in the car class, you simply say, hey, car extends vehicle. That single line gives the car class access to all the non-private variables and methods from the vehicle class. This is called inheritance. The class that passes down the properties is called the parent class or superclass. The class that receives them is called the child class or subclass. The child class gets everything that's accessible from the parent and can even add new features of its own. Let's walk through this using a complete example. We start with a base class called vehicle. Inside this class, we have two variables, speed and color. We also create a method called startEngine that simply prints engine started. Then we create another class called car, and this class extends vehicle. By writing extends vehicle, the car class now inherits all the properties and methods from vehicle. But here's the best part: we can add more things to the car class. For example, let's say a car has a unique feature like playing music. So inside the car class, we add a method called playMusic that prints playing music. Now let's create an object of the car class in our main method. When we create the car object, we can now access both the inherited method startEngine and the unique method playMusic. That's the power of inheritance. Let's understand inheritance with one more real-world example: the smartphone. Every smartphone, whether it's Samsung, iPhone or OnePlus, comes with some common features. You can make calls, send messages, use the internet and take photos. These basic features are available in all smartphones, no matter the brand, but each brand also adds its own special features, like an iPhone has Face ID, a Samsung has S Pen, and OnePlus has fast charging. Now imagine there's a base class called smartphone, which defines the common features like calling and messaging. Then each brand creates its own class, like iPhone, Samsung, or OnePlus, that inherits the basic features from the smartphone class and adds its own features on top of that. This is inheritance. We create a base class with common properties and let the child classes inherit them and extend them. You get code reuse and extensibility, just like smartphone brands reuse common phone features and extend them with their own. Let's understand this example with code. We begin by creating a class called smartphone. This is our parent class, also known as the superclass. Inside this class, we define two basic methods. The first one is make call. This simulates the ability to make a phone call and prints calling from smartphone. The second method is send message. This prints sending message from smartphone. These are two basic features available in most smartphones. Now let's create another class, iPhone. This class extends the smartphone class, which means it inherits all its methods. In simple words, iPhone is a type of smartphone, so it automatically gets the calling and messaging features from its parent. But now we add something special. Inside the iPhone class, we define a new method called useFaceID. This prints unlocking iPhone with Face ID. This is a feature unique to iPhones, not available in every smartphone. Now let's go to the main method, the entry point of the program. We create an object of the iPhone class and store it in a variable named myPhone. Here's the interesting part. Since iPhone inherits from smartphone, this one object, myPhone, can access both the parent and child methods. First, we call myPhone.makeCall. Even though this method was defined in the smartphone class, iPhone inherits it, so the method runs and prints calling from smartphone. Next, we call myPhone.sendMessage. Again, this is inherited from the parent class and prints sending message from smartphone. Finally, we call myPhone.useFaceID. This one is specific to the iPhone class and it prints unlocking iPhone with Face ID. That's it. This is how inheritance works in Java. The child class automatically gets access to all the non-private members of the parent class. You can also add more features in the child class without changing the parent. This allows for code reuse and extensibility, two major benefits of object-oriented programming. In short, inheritance lets you build upon existing functionality instead of rewriting everything from scratch. Hi everyone, welcome back. In this session, we will learn about access modifiers in Java with examples. Think of access modifiers like gates or doors. They control who can see what and from where. Just like in a house, some rooms are private, some doors are open to everyone, and some areas are accessible only to certain people. Java uses access modifiers to control access to variables, methods, and classes. Java gives us 4 levels of access: private, default, also called package private, protected, and public. Each of these defines how far your code can reach inside the same class, the same package, or across packages. In this session, we'll break down each access level one by one with simple examples and clear explanations so you can understand exactly how and when to use them. Let's get started. Let's start with the first and most restrictive access modifier, private. In Java, when you mark something as private, it means it can only be accessed inside the same class, not from outside and not even by a subclass. Let's walk through an example. We have a class called bank account with a private variable named balance. This variable holds the account balance, but since it's marked as private, only methods inside the bank account class can access it. That's why we have a method called showBalance, which prints the balance from within the same class. In the main method, we create a bank account object and call showBalance. It works fine because we're calling a public method and that method is allowed to access the private variable. But look at the commented out line. If we remove the comment and try to compile, Java will throw an error because balance is private and we're trying to access it directly from outside the class. So remember this, private means private, no one gets in. You can think of it like your ATM PIN. Only the account holder knows it and nobody else is allowed to see it. That's how private access protects sensitive data inside a class. Next, let's run the program and see the output. You can see balance is printed to the console. Perfect. Now let's talk about the default access modifier. In Java, if you don't write any access modifier, it's treated as default. And that means the code is only accessible within the same package. Let's walk through an example to see how this works. In the first file, we have a class called message. Notice something here. We didn't write public, private, or protected. So the method print message has default access. Now in the second default example file, which is in the same package, we can create an object of message and we can call print message because both classes are in the same package. But here's the catch. If we try to access this method from a class in a different package, Java will block us. Why? Because default access is package private. It's limited to the same package only. So think of it like office only access. Your teammates, your colleagues can walk in, but anyone from another office, they are not allowed. This is useful when you want to keep some classes or methods internal to a module, not fully private, but not exposed to the outside world either. Next, let's run the program and see the output. Hello from message class is printed to the console. Now let's explore the protected access modifier. In Java, protected means the code is accessible in two places, inside the same package and also in subclasses, even if those subclasses are in a different package. Let's walk through an example to see how this works. Here we created an animal.java file in the animals package. We've created a class animal with a method named sound and we marked it as protected. Now in a separate package called pets, we create a file called dog.java. The dog class extends animal. Even though dog is in a different package, it's still allowed to access the sound method because it's a subclass and sound is marked as protected. So when we run this program, the output is animal makes a sound. Now here's a helpful way to think about it. This is especially useful when you want to share behavior across inherited classes without making it fully public. Now let's talk about the simplest and most open access modifier, public. In Java, when something is marked as public, it means it can be accessed from anywhere, no restrictions. Let's look at a quick example. We have a class called greeting and inside it a method named sayHello. Both the class and the method are marked public. That means we can access this method from any other class even if it's in a different package. So in the public example class, we create a greeting object and call sayHello and it just works, no barriers. That's the beauty of public. It's like the main gate of a building, wide open. Anyone can walk in from anywhere. Now that we've seen all four access levels, let's quickly recap what we've learned. Private access is limited to the same class. You can think of it like your personal diary, no one else is allowed. Default access is limited to the same package. It's like your office, your team can enter but outsiders can't. Protected access is allowed in the same package and also in subclasses, even across packages. That's like family access, your relatives can visit even if they live elsewhere. And public, no limits at all. It's like a public website, anyone anywhere can use it. These access modifiers help you protect your data, control visibility, and write cleaner, more secure code. Thanks for watching and I'll see you in the next session. Hi everyone, welcome back. In this video we are going to learn about compile time polymorphism in Java, also known as method overloading. Let's begin with a real world example you can visualize. Imagine a person named Ravi who owns a coffee shop. Customers come in and ask for coffee in different ways. One customer says, "One coffee please." Another says, "One coffee with a sugar." And a third customer says, "One coffee with sugar and milk." In all these cases, Ravi is making coffee, but he prepares it differently depending on what the customer asks for. Same action, making coffee, different inputs, no sugar, with sugar, or with sugar and milk. This is exactly what method overloading is in Java. Let's now shift from the real world to Java code. Compile time polymorphism happens when multiple methods have the same name but different parameters, either in number, type, or order. The word compile time means that the Java compiler decides which method to call based on the method signature. Here's the official definition. Method overloading in Java means defining multiple methods with the same name in the same class, but each method has a different parameter list. Let's say we create a class called coffee machine. Inside this class we define 3 methods, all named makeCoffee. The first one takes no arguments, just makes a plain coffee. The second one takes a string argument, maybe sugar. The third one takes 2 arguments, sugar and milk. At compile time, Java will decide which makeCoffee method to call depending on the arguments we pass. Let's understand this with a coding example. We first create a class called coffee machine. Then we define 3 methods, all called makeCoffee. The first method has no parameters. When called, it simply prints making plain coffee. The second method takes one string, for example, sugar. When this method is called, it prints making coffee with sugar. The third method takes 2 string parameters like sugar and milk. It prints making coffee with sugar and milk. All 3 methods do the same action, making coffee, but they do it differently depending on the arguments. In the main method, we create an object of coffee machine. We call all 3 versions of makeCoffee. One with no argument, one with 1 argument, one with 2 arguments. Java knows which method to run at compile time based on the number and type of arguments. This is why it's called compile time polymorphism. You might be wondering, where is the word polymorphism in this? Well, poly means many and morph means form. So polymorphism means many forms of the same method. In this case, makeCoffee exists in 3 forms based on the inputs. That's what makes it compile time polymorphism. Let's quickly take one more example using mathematics. Suppose you have a class called calculator. It has a method named add. You can overload this method like this. One version takes 2 integers, another takes 3 integers, another takes 2 doubles. That's method overloading again. Same method name, different forms. Java will pick the correct version at compile time. That's the magic. So to summarize, compile time polymorphism means using method overloading, where multiple methods have the same name but different parameters. Java chooses the right one based on the inputs even before running the program. This makes your code cleaner, more readable and reusable, especially when an action can be performed in different ways. Try this out in your own project. Maybe create a class printer with overloaded methods for printing strings, numbers or objects. That's all for today's video. In the next one, we'll look at runtime polymorphism, which works differently and uses method overriding. Thanks for watching. See you in the next video. How can you make a class immutable in Java? Here is the correct interview answer. An immutable class is a class whose state cannot change after it is created. To make a class immutable in Java, the class must be declared final, so it cannot be subclassed. All fields must be private and final. No setters should be provided. And if the class has mutable objects as fields, defensive copies must be created, both while assigning them in the constructor and while returning them from getter methods. This prevents any external modification of the internal state. That is the full interview-ready answer. Now let's understand this deeply with a working example so you can demonstrate immutability clearly. We create a class named person. We want the person object to hold a name and an address object. The address class itself is mutable because it contains a field that can change. So to make person immutable, we must take extra care with the address field. Inside the person class, we declare the class final. This prevents anyone from subclassing it and adding methods that change the state. Next, we make all fields private and final so they can be assigned only once inside the constructor. There are no setter methods because setters would allow modification of the object after it is created. In the constructor, when we receive an address object, we do not assign it directly. Instead, we create a new address object and copy the values from the argument. This is called a defensive copy. It ensures that the original address passed into the constructor cannot be used later to change the person's state. Next, in the getter method for address, we again return a defensive copy instead of returning the internal address field directly. Returning the internal field would allow callers to modify the internal address object, breaking immutability. So we return a new address object every time. This combination of rules creates a truly immutable class. Now let's run a small demonstration so you can show immutability in action. We start by creating an address object with the city value set to Mumbai. We then create an immutable person object by passing this address to the person constructor. Inside the constructor, the person class stores a defensive copy of the address, not the original one. Now we modify the original address object and change its city to Pune. If the person class were mutable, changing the original address would also change the person's internal city value because both would be referencing the same address object. But since the person constructor created a defensive copy, the modification to the original address object does not affect the person object at all. Next, we try to break immutability through the getter. We call person.getAddress, which returns a defensive copy. We then change the city on this returned address object to Delhi. If the class were mutable, changing the object returned by the getter would affect the person object's data. But because person returns a brand new address object every time, the internal state remains unchanged. Now we print the internal city value stored in the person object. If we run the program, the output is Mumbai. This confirms that the person object is truly immutable. Neither modifying the original address object nor modifying the object returned from the getter changes the internal state. Hi everyone, welcome back. In this session we are going to explore a very important keyword in Java, the this keyword. You will see this keyword used a lot in Java programs, especially when working with objects and constructors. And today I'll walk you through exactly what it is, when to use it, and how it works with real examples. Let's begin. So, what is this keyword? In Java, the this keyword is a reference. It refers to the current object, the one that is calling the method or constructor. Think of it like this. If you are inside a house and you say this room, you are pointing to the room you are currently in. The this keyword does the same. It points to the current object you are working with. We use it mainly when we need to refer to instance variables, call other constructors, call methods from the same class, pass the current object as a parameter, or even return the object itself. Let's see how this keyword is used in the different use cases. 1. Differentiating between instance and local variables. Sometimes instance variables and method parameters have the same name. This creates ambiguity. To resolve it, we use this keyword to clearly refer to the instance variable of the current object. It helps avoid naming confusion, especially inside constructors or setters. Let's look at an example to understand this better. We begin with a class named student. Inside the class, we declare a private instance variable called name. Then we define a constructor that also takes a parameter named name. Here's where the confusion happens. The instance variable and the parameter both have the same name. To avoid that ambiguity, we use this .name equals name. This .name part refers to the instance variable. The plain name on the right refers to the constructor parameter. Then we have a display method that prints out the value of this name. In the main method, we create a new student object and pass John as the name. Then we call the display method. Let's run the program and see the output. As you can see, the output is displayed. Name John. It correctly prints John because this .name equals name assigned the constructor value to the objects field. This is how we use this keyword to clearly refer to the instance variable of the current object. 2. Calling current class methods. The this keyword can be used to call another method from the same class. Let's see an example of how that works. Here we have a class called calculator. It has two methods, add and compute. The add method takes two numbers and prints their sum. The compute method calls add using this .add 510, which means we are calling the method from the same object. In main, we create an instance of calculator and call compute. Let's run the program and see the output. There we go. The output sum 15. So what happened here? Compute called add 5 10, which printed the result 15. The this keyword was used to refer to the current object's method. 3. Invoking current class constructors. Sometimes we want to reuse one constructor from another constructor within the same class. Instead of repeating the code, we use this to call another constructor. This is known as constructor chaining and is very common in Java to keep code clean and DRY. Let's take a look at an example. We define two constructors, one with no parameters and one that accepts length and width. The no argument constructor uses this 0, 0, which calls the other constructor with default values. That's called constructor chaining, and this helps us link one constructor to another. In the main method, we create two rectangles, one using the default constructor and one with real values. Let's run the program and see the output. As you can see, the first rectangle has default values thanks to this 0, 0 call. The second rectangle uses the values we passed, 10 and 20. Next, fourth use case, passing the current object as a parameter. You can pass the current object itself to another method using the this keyword. This is useful when methods need to work on the calling object or when passing it to another class. It's a great way to share the state of the current object without creating new references. Let's check out an example of this. We create a class named person with name and age. We define a method show that takes another person object as an argument and displays their data. Now here's the trick. In invoke show, we call this dot show this, passing the current object to the method. In main, we create a person named Alice, age 30, and call invoke show. Let's run the program and see the output. Output name, Alice, age 30. So by passing this, we pass the same object to another method. This pattern is very useful when working with callbacks or APIs that expect an object reference. Next, the fifth use case, returning the current object. You can also return the current object from a method using this keyword. This is mostly used in builder patterns and method chaining where you want to perform multiple actions in a single line. Returning this allows one method to be immediately followed by another. Let's walk through an example to understand this clearly. We define a method setX that sets a value and returns this. That allows us to call setX.display in one line. This is called method chaining. In the main method, we create the object, set the value to 10 and immediately call display. Let's run the program and see the output. Here is the output, x 10. This is how builder style patterns are created in Java using return this. Let's wrap up. The this keyword is like your current identity in Java. It always refers to the object currently in use. We use it for assigning fields, calling methods, chaining constructors, passing objects, or returning the current instance. This keyword helps us write clean, readable, and chainable code, especially in OOP and design patterns. That's it for this lesson. Thanks for watching and I'll see you in the next one. Hi everyone, welcome back. In this session, we are going to learn a key concept in Java inheritance, the super keyword. Now think of it like this. When a child wants to refer to something from their parent, like their name or a shared habit, in Java, that's exactly what the super keyword does. It helps a child class access things from its parent class. So what exactly is the super keyword? In simple words, super refers to the immediate parent class of a subclass, and we typically use it in three situations. First, to access parent class variables, especially when they are hidden by variables in the child class. Second, to call parent class methods if they've been overridden. And third, to call the parent class constructor. We'll go through each of these one by one with complete code examples and clear explanations. Let's begin with our first use case, accessing parent class variables using the super keyword. Imagine you have a parent class that defines a variable named name. Then you create a child class and it also has a variable called name. So which one does Java use when you access name? Let's look at the code. We have a parent class with a name variable set to parent. Then we have a child class that extends parent and it also has a name variable, but this one is set to child. Inside the child class, we define a method called print names. In that method, we first print name. Since the child class has its own name variable, Java uses that and it prints child. Then we use super.name. This tells Java, hey, don't use the child's version, go to the parent class and use that one instead. So it prints parent. When we run the program, the output is child, parent. That's how super helps us access a variable from the parent class, even when it's hidden by the child class. Now let's look at another powerful use of the super keyword, calling a method from the parent class especially when it's been overridden. This is useful when you want to extend the behavior of the parent method, not completely replace it. Let's walk through the code. We have a class called animal with a method named makeSound, which simply prints animal makes a sound. Now the dog class extends animal and it overrides that method. In the dog version, it first prints dog barks, but then right after that it calls super.makeSound. And what does that do? It goes back to the parent class, the animal class, and runs its version of makeSound. So when we run the program, the output is dog barks, animal makes a sound. Even though the child class overrides the method, super makeSound lets us bring back the parent's version and use both together. This is helpful when you want to extend your parent's logic instead of throwing it away. It's like saying, do what I want first, but also don't forget what my parent used to do. You will often see this in real-world inheritance when the base class sets up some common behavior and the subclass builds on top of it. Let's look at one more important use of the super keyword, this time to call a constructor from the parent class. This is especially useful when the parent constructor does some setup that the child class depends on. Let's go through the code together. We have a vehicle class and its constructor prints vehicle constructor called. Then we have a car class that extends vehicle. Inside the car constructor we write super, and that's a call to the parent class constructor. It ensures that before the car does anything, the vehicle constructor runs first. After that we print car constructor called. So when we create a new car object in the main method, the output looks like this. Vehicle constructor called car constructor called. This shows that the parent constructor runs before the child constructor. And with super, we control exactly when that happens. A few things to keep in mind. 1. Super must always be the first statement inside the child constructor. 2. If you don't write it explicitly, Java will insert it for you automatically, but only if the parent has a no argument constructor. And 3. If the parent class requires arguments in its constructor, then you must call super with those arguments manually. So use super when your child class needs to reuse or extend setup logic from the parent class. And that wraps up our 3 main use cases for the super keyword. Let's wrap this up. In this session, we learned about the super keyword in Java and how it connects a subclass to its parent. We saw how super.dot variable lets us access parent class variables even when they are hidden by the child. We used super.dot method to call overridden methods and bring back the parent's behavior. And we used super to call the parent class constructor, making sure any setup in the parent runs first. These are simple but powerful tools when working with inheritance in Java. Once you understand how super works, your code becomes more organized, more reusable, and much easier to manage. Thanks for watching, and I'll see you in the next session. Can you override a private or static method in Java? Here is the correct interview answer. You cannot override a private method in Java because private methods are not visible to subclasses. Overriding requires the method to be inherited and accessible in the child class. Since private methods are completely restricted to the class where they are declared, the subclass cannot see them, cannot inherit them, and therefore cannot override them. If a subclass defines a method with the same name and signature as a private method in the parent class, it is treated as an entirely new method that belongs only to the subclass. There is no relationship between the two methods, and the JVM does not consider this overriding. Next, static methods also cannot be overridden. Static methods belong to the class itself, not to individual objects. Overriding works only with instance methods because instance methods use runtime polymorphism. Static methods are resolved at compile time using the reference type, not at runtime using the object type. So when the subclass declares a static method with the same signature as the parent class, this is not method overriding, it is method hiding. With method hiding, the version that gets executed depends on the reference type you use, not the actual object. So the complete and correct explanation is private methods cannot be overridden because they are not inherited. Static methods cannot be overridden because they are class level and resolved at compile time, and only non-static inherited accessible instance Methods participate in actual method overriding in Java. Now let's demonstrate this using a working example that you can run. This time both concepts will be shown clearly with correct output. The parent class contains a private method named message and a static method named greet. The child class also contains its own private message method and its own static greet method. To actually demonstrate the private method, we provide a public method called callMessage in each class. This method simply calls its private message method internally. This is the only legal way to invoke a private method from outside. Now let's run the program and walk through the output. First, we call the static method greet using a parent reference that points to a parent object. The output is parent static method. Next, we call greet using a parent reference that points to a child object. Even though the object is a child instance, the output is still parent static method. This clearly demonstrates that static method selection is based on the reference type, not the actual object. This is why static methods cannot be overridden. Now we call greet using a child reference pointing to a child object. The output becomes child static method. This is method hiding in action. The method chosen depends on the reference type, not the object. This behavior is the opposite of overriding. Now let's move to the private methods. We cannot call a private method directly, so we use callMessage, which internally calls the private message method. When we call p.callMessage, the output is parent private method. When we call pc.callMessage and pc refers to a child object, the output is child private method. This happens because callMessage is a public method and public methods can be overridden. At runtime, Java checks the actual object, sees that it is a child object and executes child's call message. Inside that method, child's private message method is called. Because private methods are not overridden, each class calls its own private version. Now when we call c.callMessage, the output is child private method. Hey there everyone, Ramesh here, back again with another video. In this video, we'll quickly discuss one very important Java OOPS interview question, that is why Java is not a purely object-oriented language. Well, this question may be, especially asked for a fresher in the Java interview. Alright, and if you are a fresher, then make sure that you have an answer for this question. Well, let's understand why Java is not a purely object-oriented programming language in this video. Well, look at here, these are the 7 qualities. Well, whenever we say a programming language is a purely object-oriented programming language, then that programming language should satisfy these 7 qualities. Alright, the 7 qualities like encapsulation or data hiding, inheritance, polymorphism, abstraction, all the predefined data types are objects in that programming language, and all the user-defined types are objects in that programming language, and all the operations or methods that perform the objects must be only through methods exposed at the objects. Well, these are the 7 qualities the programming language should satisfy in order to call that programming language as a purely object-oriented programming language. Well, let's compare these 7 qualities with Java programming language and let's understand why Java is not a purely object-oriented language. Well, you can see here among these 7 qualities, the 5th one and 7th one. Well, in Java, we have 8 primitive data types, right? Int, char, long, double, float, short, right? So these 8 primitive data types are not objects in Java, okay? And we can call these primitive data types without using objects in Java. Alright, that's the reason. This is the first reason why Java is not a pure object-oriented programming language. Okay, and 7th, you can see the quality. All operations performed on objects must be only through methods exposed at the objects. Well, in Java, we typically create a class and we define the instance variables and methods. And then we create an object of the class and then we call the instance variable and methods using object, right? But again, in a Java, you can see here we have static variables and static methods. In Java, we can call static variables and static methods without using object, right? So that's the reason, this is the second reason why Java is not a object-oriented programming language. Because a pure object-oriented programming language, should only access all the methods or variables through objects only. Okay, but in Java it is possible that we can access static variables and static methods without using objects. Alright, great. Well, let me demonstrate these reasons with an example so that you will understand better. Well, here you can see we have a class, within a class main method, and within a main method I have declared and initialized these primitive data types like integer, byte, short, long, double, float, boolean, char. So these are the 8 primitive data types in Java, and these are not objects, right? And we can access these primitive data types directly. Okay, we are not using objects to access these primitive data types, right? That's the reason, this is the first reason why Java is not object-oriented programming language. Well, if I run this program, it should work properly. There we go. This is the output of this program. You might be wondering, we have wrapper classes in Java, right? Correspond to each primitive type. So by using wrapper classes, can we, make Java as a pure object-oriented programming language? Well, no. We cannot, use wrapper classes to make a Java as a pure object-oriented programming language, because wrapper classes under the hood uses primitive types only. For example, look at here, this is a code snippet. Let me uncomment it, and you can see integer is a wrapper class for int primitive data type. And if you can see the description of this integer class over here, integer class wraps a value of primitive type int in an object. Well, this class, wrapper class, is just a wrapper on top of primitive type int. Okay, it does not replace the object. It internally uses primitive type only. For example, if you calculate these two numbers, then behind the scene Java internally uses primitive type int to calculate these values. Okay, so there is a concept like in Java, boxing and unboxing, right? So Java internally uses primitive types to perform operation, right? It means that you cannot use wrapper class to make a Java as a pure object-oriented programming language, because under the hood Java uses primitive type to perform the operation on primitive data types. All right, so this is the first reason, that is, in Java we have 8 primitive data types, and these are not the objects. Okay, so this is the first reason why Java is not a pure object-oriented programming language. And second reason is, we have static variables and static methods in Java, right? And we can access them using without object. For instance, well, look at here, I have created one static variable message, and I can access this static variable without using object. So look at here, this is the system.out.println, and directly I am accessing static variable message without using any object. And again you can see the static method, and this static method I am going to access here without using object. So it means that in Java we can access static variables and static methods without using objects. So this is the second reason why Java is not a pure object-oriented programming language. If I run this program, it should work. There we go. Alright, so these are the two major reasons why Java is not a fully object-oriented programming language. Alright, so in the interview, in order to answer this question, make sure that you will provide this kind of explanation. Alright, I hope you understood why Java is not a fully object-oriented programming language, and I have demonstrated with an example so that I believe that you understood why Java is not a pure object-oriented programming language. Alright, great.